years, and so I'd like to tell you a little bit about where we see things going and what's happening. So first of all, if you want to know where a TSV is, it's probably in your pocket, a through silicon via. Because if you're using one of the new iPhones with a fingerprint sensor, there are 29 TSVs in that, in case you didn't know. And those are being used basically to connect a sensor and a logic. And that's becoming fairly common. It helps reduce the size, improves the performance, moves everything in the package. So there are a number of reasons for the adoption of that. And we'll see some other companies adopting that kind of structure for the fingerprint sensors in these high-end phones. Also, if you look over here to the right, that's one of the early Sony image sensors with the stacked, the image sensor and the logic, and those were connected, some of the early ones with TSVs. Some of the newer ones are using some of the copper-to-copper direct bonding, but it looks like there may be still some TSVs on the sides of that part. So if you're looking for memory and logic stacks in your phone, you won't find those. And at the end of the presentation, you'll understand what we're doing instead with that. And that's where I want to talk a little bit about why we're seeing the developments in fan-out wafer level package. But what's happening in the mobile space is the falling prices for the handsets themselves really create a lot of price pressure that makes it very difficult to adopt new technologies in the mobile space. And also the other thing we have going on that we don't have in a lot of other spaces is these product ramps. Down here is a little picture cartoon that shows you how the product ramps for the iPhones have changed over time. There used to be long product ramps, long product life, but now the product ramps are shorter and shorter till it's like a straight, almost a straight up line. And that creates havoc for the people who design the ICs that go in that package them, for the infrastructure for the whole industry, and it just really causes us, I mean, that's really why I think we're all living in this era where we feel like we're just worked to death and exhausted. It's because of these steep ramps in the mobile space, so blame it on that. But it also means you have to have a low-cost solution and an infrastructure ready to meet the ramp. So now let me switch gears for a second. I want to talk to you just a minute about some of the challenges for high-performance systems. We're really entering a new era in our high-performance systems, things like the servers, the enterprise, the cloud, the client, networking systems. And what we hear a lot of talk about is Moore's Law, which I like to say is really an observation. What it's always meant is we have density scaling, speed scaling, power scaling, and cost scaling. But what's happening is with our higher cost of the lithography for the next generation silicon nodes, we're really stuck where we can't do the things that we used to do. We can't just count on this scaling to bring us lower cost parts and to help us. So what we've seen is some work with stacking transistors and other silicon developments that are buying us some time. But it's that extra future cost of the lithography, more and more expensive to develop those next node chips, that's causing the industry to have to rethink the way it does things. And so what's happening is the foundry level is now being gated by what's happening in the packaging side, because the packaging side is the answer of how to cost reduce these things. It's the answer of how to deal with the severe interconnect delay. It's how to handle the bottlenecks for the higher bandwidths. It's where we have to deal with the device latency issues, power management, delivery, and distribution needs, and form factor. All of that has to be coupled in with what we're doing in the fab side. And we're going to have a lot more reliance on the back-end package design than we have had in the past. So I'd like to say that in the silicon interposer, we're really at the beginning of an era. And it's really the high performance end of these things. You know, we saw the first FPGA shipments that started back in really in 2012, tail end of 2011. But it started out with Xilinx. And I don't know if you can see this picture up here at the top, but there are 4 partition slices. And if any of you have anybody designed FPGAs before, you know what the yields are coming off those first trip. It's a very, very large die. And so your defect density just kills you. Well, what Xilinx was able to do with this new partitioning design was they were able to design it into slices. And they actually bend those slices and put the best performing slices together to communicate through this the line and space on the interposer, through the RDL layers, on a silicon interposer, communicate those chips, and then they function like a single chip. And it's giving better yield, so you can almost pay for the silicon interposer with your yield improvement, and it's better performance. As a matter of fact, when I was at Xilinx, when they first introduced this, the electrical performance and all the performance was just surprising. It even exceeded what they expected from the modeling. So the partitioning idea is a very, very important idea. And now this was just a homogeneous type of chip, but this is being applied also to heterogeneous integration as well. But we also are expanding from just the high performance FPGAs to now in the mid-range products in the Xilinx family. We're also seeing ASICs designs move into production on silicon interposers, and we've seen already some graphics plus stacked memory, things like gaming. This is fairly low unit volumes, but these are high dollar values. And so some of this stuff, it always starts at the very high performance, lower unit volumes, but it's high dollar value stuff. And we're continuing to see applications that will be coming up in network systems and future servers. And these are the applications that really have to have a high performance solution. The cost-benefit analysis allows the adoption of something like a silicon interposer. So it's a very important area. And down here, I'm going to talk to you in just a minute about AMD's entrance into this, which is, of course, one of our local companies. Now, let me remind you what was involved in introducing that very first product from Xilinx. It started back in 2006 with the development. But remember, I said it was 2012 before we went to volume production. That's 6 years. How many people's companies want to stand around for 6 years while you develop something like this to introduce it? Anybody company willing to stay around and fund you for that long? It's hard to do that. But Xilinx was really thought about it ahead of time and really saw that they had the vision to do this. It also meant that they had to go buy a couple of software companies to get this done, and a lot of engineering work in this, but it really paid off. So what we have now is in the next silicon nodes, we're seeing 28 nanometer where it was first introduced, 20 nanometer and 16 nanometer nodes, 19 packages when I checked the other day in the 20 nanometer node, 18 packages in the 16 nanometer node. And many of these 20 nanometer and 16 nanometer products are really larger than a reticle. And so basically there's some very interesting reliability papers. This is done with what TSMC calls their CoWoS process, which is the chip on wafer on substrate, where all the die are put on the wafer, and then it's diced up and put on the substrate. We're using micro bumps, typically copper pillars, to connect that die to the silicon interposer, and then a regular flip chip, what people like to call a C4 bump, to connect that to the laminate package at the end. So we see this continuing. Here's an example of one of these slices from an FPGA slice with some of the serial transceivers. We're seeing it in heterogeneous integration as well now. And the latest introduction from AMD with a silicon interposer is the Fiji solution for the graphics market. This is using a large ASIC, which is mounted in the center of a silicon interposer with 4 high bandwidth memory stacks with 4 DRAMs each and a logic die mounted next to the interposer. So as I showed you from the other drawing, the logic die is in the middle and one of these each stack on a corner. And so there are about 200,000 interconnects in the whole module, including the copper pillar micro bumps and the C4 bumps that connect it to the laminate substrate. The silicon interposer in this has 65,000 TSVs. So in your spare time, you could get one of those and go count it. But this is a phenomenal engineering development. This required a lot of partnership with the design team at AMD, with the OSAT partners, with the foundry partners, with the silicon interposer partners, and it took a lot of work to really achieve this. So it should really be looked at as really an engineering feat. Now, the interposer options, as I mentioned, silicon interposer are in production today. We're seeing more and more designs. We've got the AMD graphics cards, maybe some future CPUs from AMD. We've got a very high-end silicon interposer that's been for NVIDIA's some high-end applications that'll be coming out this year. And we have other network and server products that will be using silicon interposer. And we got our infrastructure established. People like Global Foundries, Interterra, TSMC, UMC. UMC is currently supplying that interposer for the AMD product. We also have people trying to come up with lower cost solutions. Some of it without TSVs in it, some of it with things like what Intel is doing with their EMIB, which is a silicon bridge and an organic interposer. And where the substrate supplier is the one that embeds the little silicon bridge. We also have people trying to work with organic interposers, where they're going to use build-up technologies to make finer features, and we're seeing some people demonstrate less than 5 micron line in space with that. They're using basically existing infrastructure for the laminate substrates. We really have to get the yields up to get the price down. It's not like making a silicon interposer where you can do sub 1 micron line in space and not really trouble yourself too much. But the suppliers that are working on the organic interposers are people like Ibiden, Kansas, Kyocera, Simco, Shinko, and Unimicron, those companies that you're very familiar with in that. Now, if we look at what kind of designs are coming up, eSilicon says that they have a number of interposer programs, both in organic interposers and in silicon interposers, and 2 of these designs are going into production in this year. And when I visited TSMC a couple of weeks ago, they told me that they've got a lot more designs coming out in the CoWoS process using their interposers, silicon interposer structure for those products. So I think what you'll do is you'll continue to see in the high performance space many more designs over the next few years. So we're really starting in this era. Now, there are people coming up with ideas like Amkor Slim. Xilinx has something called Slit. And these things are designed to where you're coming up with an RDL with fine feature sizes without TSVs. And this is a cost reduction point. Now, I haven't seen any of these things in product, but I do hear people talking about this as a cost reduction measure. What Intel's idea is a cost reduction measure is this thing called the embedded multi-die interconnect bridge, which is really available to the 14 nanometer customers at Intel's foundry. And the first one being Altera, which they subsequently purchased the whole company, and we're expecting shipments from some of those FPGA applications in this technology. Now, what the idea is as you can see, there's these die that are going to communicate through this little piece of silicon that has fairly fine feature sizes, and it's only that density of the silicon that's embedded in the organic substrate. So they're micro bumps, they're small micro bumps that are being used to attach to that silicon bridge that's in the interposer. And then on the rest of the chip are larger bumps, and those are just going to be mounted on the regular organic interposer. So the substrate supplier is going to make this substrate, and then Intel is doing the assembly. The assembly is kind of a tricky part, so that's what Intel is really going to work to do internally. And it's considered considerably less expensive because there's only using that very small area for the high density silicon, and there are no TSVs in this solution. So I'd like to think of 2015 as kind of where we started seeing the year of the memory stacks with TSVs. So probably some of our larger high volume applications are the memory stacks. And I've highlighted the fact that this is a new memory architecture design. We have things from Tezeran shipping in production. We had Micron's introduction of the HMC, the hybrid memory cube, which started in about 2015 with many designs with the Samsung RDIMM with the stacked memory for servers, and also now some DRAM stacks coming from Samsung. And of course SK Hynix with the HBM that's being used in AMD's graphics card application. This is where the stacked die are mounted on an interposer. The difference between the HMC and an HBM, for those who are trying to figure that out, is that the HMC is actually mounted on a substrate, so it's tested like a traditional package, socketed like a BGA package, and then it's mounted on a printed circuit board. The HBM solution is actually mounted, there's no laminate interposer in it, it's mounted directly on a silicon interposer. So the HMC solution for some of the high performance applications, it's tested as the BGA, assembled on the product board, but the design architecture is very different. I like to call it the DRAM's in charge. Normally the processor has a lot more responsibility, but in this design, I think it's really, for a simplistic point of view, it's kind of the DRAM guys get to design and control a lot of stuff. So some people don't like that as much, but it's more power efficient, it's got a smaller footprint, it does offer an increased bandwidth solution and reduced latency. But these are all new architectures, so you really have to learn how to design with this stuff. And there's a number of applications. I think probably some of the most commonly talked about one is the Knightsbridge from Intel. Xilinx is also, and others are also talking about using silicon interposers with each HBM stacks. And you can see from this cartoon of how it might look when it's communicating with an FPGA, where you have the high density stack of memory and then the FPGA, and you're communicating through that, basically the patterns on the top of the silicon interposer between the two. We also have the future, that's interesting. So we have future projections of where HBM systems and memory architectures might be used. This is from SK Hynix. They're arguing that this, obviously what we've talked about is the high performance servers, networks, and graphics. We're talking about client, maybe notebooks. I think this is a little bit aggressive in the use of it in mobile and wearable, but we'll see, maybe out there at some point in time. So the question is, where should the industry expand and focus on 3D IC with TSVs? First of all, with the EDA tool availability, we have help on the way. And there's a number of things that you can see as you go out through this show. We have major improvements in the wafer thinning, debonding process with new materials, new process steps, and we've learned a lot. For stacked die assembly, we've had some yield improvements in that, but we still need more work. We have improved test methods for known good die, known good substrates, and known good interposers. And we also have to work a little bit more on our thermal solutions. Even within a memory stack, that's challenging. We need to improve the yield of this whole process because that's really where we produce cost. So if we look at some of the design guy as he thinks, this is my poor confused man. So poor confused man has a lot of stuff to deal with. He's got process and architectural choices, and he's really got to figure out what is the stack orientation, what the technology nodes would be, the package types, the number of TSVs and the locations, keep out zones, the local or global chip package interaction. Yep, we have to evacuate. Well, come back and I'll finish this. Okay, thank you guys for coming back. I guess this was really a hot talk, no pun intended. So anyway, our little man is very confused about all his choices, so what he needs is a good EDA tool. But the challenge with for EDA tools is that it's the word A, automation. It's very difficult to decide what and where to automate because there's a lot of different requirements and solutions, especially to support this 3D IC technology. Because we're talking about floor planning, routing, signal and power integrity, thermal aware designs. So for the large memories that are stacked with TSVs like HMC or HBM, they say they really didn't need a lot of additional tools beyond the SPICE simulators. They require redundancy, they have built-in self-test and repair, require design for test, and remember all these products are new architectures. But the adoption of 3D IC really requires a new system architecture, and this is the key part. It's designed really moving forward in almost everything we do in our industry. It's really designing from the system level. Co-design is the word that is very, very important. It's required. It's not optional. It's going to be required as we move forward, whether we're talking about 3D IC or whether we're talking about a lot of other things. So one of the tools here that you'll see in the Mentor Graphics booth is Expedition, which is really nice because it's the integration and co-design platform for IC package and PCB. So what that allows you to do is combine, look at everything in the toolbox and help you from really a co-design, a true co-design solutions. Some of the other challenges that we're dealing with in 3D IC are the assembly challenges for things like stacked memory. Think about it. We've got a bump pitch that's typically 40 micron or less, a copper pillar, maybe some other bump metallurgies. Our micro bump variation could be a challenge if we're not uniform We also need a higher accuracy bonder, typically a plus or minus 2 micron bonder with that. But these are, the trade-off is they're very accurate, but they're slow. So we're hoping for improved tools that are faster. These things cost about $1 million or so each. And so we have to have very, very high yield in that stack because you don't want to throw away something expensive like this. Also, we're doing a lot of work in the underfill area with developing new underfills for these parts. A lot of it's been capillary flow, typically in our microbump, but we've seen non-conductive paste, and a lot of people are looking at non-conductive films, and some people are already starting to use that. Test issues with 3D-IC. I like to think of this thing as what we've been doing is stack and pray to deal with our accumulated yield loss. You know, if you look at it over time, this is some analysis that Paul Franzen had done, basically some of our 3D TSV memory, like I mentioned, HMC, you test that in the package before you commit that to the printed circuit board. But you really, if you test 100% of these things, it's very high cost. That's why you have to have so much built-in self-test, things like that. There's a question about whether we test through the TSV microbump interface or around it. As if you're talking about testing a 10,000 microbump array, it's going to be very difficult and potentially very, very expensive. So we've got a lot of issues to deal with this. So a lot of people talk in this space about more built-in self-test, redundancy, and self-repair. Now, one of the biggest issues in the 3D-IC space, and I'd say this is a true showstopper, is really our thermal issue. Your low-cost thermal solutions have to be available, and the key word is a low-cost thermal solution for memory and logic to see widespread adoption. So that's why you still stick to the current POP solution. The reason it's an issue is because if you think about it, the logic has hot spots. The logic chip is going to be hot. It's going to be potentially overheating, and memory would be sitting theoretically on top of that. So the memory would get heated up past its spec by the manufacturer, and so it would cause it to have problems. And so that is the problem. When you put memory and logic together, or even logic and logic together, the hot spots would heat the chip up above it. So we don't have a good thermal solution. And when we thin the chip down, it creates extreme conditions for on-chip hotspots. So we've got to have some lower power designs. We really have to have new architectures in this. And you remember when I talked about the mobile space, all right, at the very beginning of the talk, for those who were here. The application processor trends, many people are talking about fan-out wafer-level package. And I mean specifically the Info TSMC process that's the worst kept secret in the industry, that's going to be in the next A10 processor for the iPhone. So basically, the application processor and memory, so here's the top memory package, here's the application processor. That's the way we've been doing it mostly in the high performance area. The memory's wire bonded, it's in a package, it's tested, it comes in, and you stack that on top of a logic die that's typically flip chip to the substrate. Now that's pretty thick. So what we want is we want a thinner package solution. So if we went with a 3D-IC with a memory and logic stack, that would actually give us the ultimate in package height reduction. It would actually give us the best electrical performance. But it continues to be pushed out. We haven't seen it, we won't see it for a while because of thermal issues. There's no way to deal with the issues of thermal here. The cost issues associated with this technology, the risk, and the business issue of coupling memory and logic together in the design. We don't see silicon interposes in this space because basically they're too expensive for many of the mobile products. Remember at the start of the talk I told you that application, ASPs are falling for some of the handsets. They're really cost sensitive. So we want to continue with POP in a high-end smartphone. Option one is you'd continue with this top package, you just thin everything down, thin the substrate down, and you get a little bit lower profile. Option two, embed the application processor in the bottom laminate substrate. That has a lot of challenges as well. Option three, and this is what the TSMC Info is, this is this bottom picture, where Info, there is no package substrate. It's the RDL layers and thin film that are creating the structure, and the die is attached to that with a very small post on it, basically almost no bump. And this is makes that package very, very thin. It also, if you look at the presentations from last week at TSMC, gives you incredible electrical performance, thermal performance, because there's no substrate anymore. You've got a direct heat path to the printed circuit board. But this is only achieved with a very clear co-design all the way from the package to the foundry and the system level. So this is a very, very important development that we'll see coming out this fall. There's also some other new formats that are being talked about in fan-out, maybe some RDL first, chip lasts, what Amcor calls a SWIFT, and we've talked about a lot of those in some of our publications. But basically the bottom line is this is a low profile, high routing density. You can do 2-micron line in space in this particular info package that's being designed for the A10, and it's basically system integration with competitive cost. It's not what we'd get if we did a true 3D IC, but it's the best we can do for now. So in conclusion, I'd like to say that 3D ICs are in production with image sensor and logic. We have a lot of stacked memory in the very high performance space. The industry's working to resolve a lot of our issues. We've seen a lot of 2.5D silicon interposer production for GPU. We'll see it in CPU. We're seeing it in ASICs. We've got some low-cost alternatives coming along with the organics, with the Intel EMIB. We're still looking at our business models. They're settling down now. Cost remains an issue, new architectures, and you better have the word co-design in your vocabulary. But let me close with this remark. New architectures take time to develop. It takes a long time. Be patient. These things, look how long we went from the first memory, 12 years. From memory R&D to product out the door. It took a very long time. Now, the next things may be faster, but just be patient. Thank you very much.